Alright, here's a problem I specifically skipped over a lot. And it's a simple one. It's if you have a half circle that could be modeled. Sorry, that was kind of bad drawing. That could be modeled by square root of r squared, where r being your radius, minus x squared. That could be modeled by that. That could be your function here. Let's make that r a different color. There we go. So that's how we can model each one, and that would be centered right here. Cool. So that's nice, but if you integrate that'd be, I don't know, just pi r squared divided by 2, because that's a half circle. Now if you made this value 2, if you made it 2 square r squared minus x squared, well, that would take each of these lengths and double it over the other side, and so you could expect that gives us a full circle. So even more, you could expect that if we integrated this from, that'd be a negative r, that'd be the back r, and this would be the forward r. If you integrate it from there to there, dx, you can expect that is going to be an area of pi times the radius squared, all divided by, no, not divided by anything, just pi r squared. I was going to say divided by 2. This would be pi r squared divided by 2 because it's half a circle, but yep. So just pi r squared. Easy as that. Except for, is it easy? How can we know that for sure? How can we be confident in the answer? Because we didn't really solve an integral here, did we? We kind of just used some basic logic about that we were told in early on. I don't know when you're told pi r squared, or if you've ever been told pi r squared, but that formula, where does it come from? So it's existed for a very long time. Greek times, of course, have known this, even before Babylonians were, I believe, seen using this formula to calculate the area of a circle. However, they've always tried categorizing pi, and we know r squared as the area of two r's multiplied. So if you have two distances, it's that area. And then pi is the thing that kind of molds it into a circle. Right? That's kind of the idea here. You kind of take that square of r by r and make it 3.14 times bigger, about that much. And you can kind of see that this is about a little less than less than 4 squares of r by r. Yeah, so if you cut off about, I don't know, whatever 4 minus pi is, that would give you these areas. All right, so that was known, and there's always kind of ways you can do it. And I think we proved this formula roughly, no, pretty well actually, in the other videos, where we took a small triangle, we used a formula for area, and we were able to find that. Well, yeah, you could there's so many ways you can integrate something. You could see a circle, and you could integrate it by taking all these slices, all right, and then spinning it around. And so you're integrating each of those pi slices. Let's write it as pi slices. Pi and the word pi have so much in common. If you integrated all of those from 0 to 2 pi, being a full circle, yeah, you would find the area of that guy. Or we could do the way I have clearly skipped over, which is add up all these small rectangles along this equation until it goes completely across. So let's do it. The scary problem that is this. All right. Why is it scary? Well, have a go yourself. All right. Before I even write anything, think, how would I solve this? Well, you're probably thinking the wrong route. And here I'll show you why. So you have 2, let's figure the 2 out right now. then we have r squared minus x squared. Your first intuition is probably, okay, just, if this was derivative, really easy because you just derive the inside, derive the outside, and then you multiply them. Easy. But this guy, not so easy because integrating is a different little beast right here. That's a weird way to word it. Oh yeah, negative r to r. You have to use a really interesting route. So how are you thinking to start this? Well, it turns out one of the best things you can do to yourself, for yourself, not to yourself, is rewrite the inside of that guy. R squared minus x squared is the same as, what happens if we divide both by r squared? Well, if we divide both by r squared, we'd have to factor in r squared out. So this divided by r squared is 1. This divided by r squared is x divided by r. Let's put that in parentheses. Both of them are squared. So this can be rewritten as this. Therefore, if we square root both of them, that gets rid of the squaring here. And so now you're left with r times the square root of 1 minus x divided by r squared. Why is that better? Well, it turns out factoring that out actually helps you out a little bit. That didn't really answer why is it better. Alright, so that's still from r to r. And now we have this friendly giant x divided by r squared. And still the x. Alright, so we factor that r out. Now, anything else we can do? This is where u substitution kind of comes into play. What you really want here is to convert this in a way, sorry, I'm thinking here. You want to convert this in a way that gets rid of the square root. Alright? And what is, bear with me here. 1 equals cosine squared of theta plus sine squared of theta. Alright? Let's subtract sine or cosine. Let's do cosine. Cosine, sine, cosine. No, let's do cosine. Wait, why did I say that? Yeah, let's keep cosine on this side. So we have cosine squared theta, subtract sine squared. And again, the squareds do not have to go there. They literally mean that whole thing squared. And check this out. Cosine theta can be rewritten as the square root of 1 minus sine squared. You probably already knew this. But if we could replace x divided by r with sine of theta, then this would get a lot easier, wouldn't it? Turns out you can definitely do that. This is going to be incredible. You should be so excited because this is no longer a super hard problem. This is possible. We can do this. So let's replace x divided by r with sine of theta. Now, if we're going to do this in an integral problem, we have to write its derivative on the outside. All right, that's the only sad little part. If we're going to do this substitution, if we're going to replace this, we have to have the derivative on the outside back here, multiplying it. All right. So we know if we take a derivative of this guy with respect to x, you get 1 divided by r times dx. Now you know if you replace this guy, this would just be cosine. That's easy. So you get cosine theta, and then this guy would be d theta. All right. Let's simplify it. Let's just get dx by itself because we know dx is just dx. So dx, let's multiply by r. We have r cosine theta equal, dx equals r cosine theta d theta. All right, look. Hey, we got an extra r on the outside. It's like we're feeding it r's. All right, so if we replace dx with this guy, we get an extra r on the outside. So now we got integral of 1 minus sine squared theta, because if x divided by r is sine, then that's 1 minus sine squared, right? Squared. And that is multiplied by r cosine. We already multiplied by the r, by the cosine, theta, and d theta. All right. Nice. Except for there's another thing we have to change, and that's the bounds. No longer are we working on terms of x divided by r from negative r to r. We're now working on sine over here. So we can rewrite this guy to solve. This is when x is equal to negative r and when x is equal to r, right? So this value here is r divided by r has to be equal to sine theta. All right? And so r divided by r is 1. When is sine theta 1? What value of sine will get you, what angle will get you a value of 1 when you plug into sine? Well, sine is the y values. If you look, if you go up to pi over 2, check that out. That would get you a value of 1 right here. Pi over 2 gets you 1. That's all that was about. Check that out. We solved it. So theta has to be equal to pi over 2 on top. Now you can probably guess the other one. When is it equal to negative 1? Because negative r divided by r is going to get you negative 1. When is sine going to be equal to that? Well, the angle has to be, it's either negative pi over 2, go backwards, or 3 pi over 2. I prefer negative pi over 2 here. So let's do that guy. Cool stuff. We converted here. Now we can continue working with this. Let's move on to the next page. So we have all this guy. This is going to be the ball area of a circle, which is a formula we overuse. So it's actually good that we're finally doing a really rigorous, well, it feels rigorous, proof of this. So we have that negative pi over 2, the positive pi over 2, and the 2 right here. All right, what can we do here? So we know we can, this guy is equal to cosine, just a regular cosine. So this is cosine times cosine, which is cosine squared. Cool. So we are now integrating, let me move my markers. We are now integrating on different bounds and a slightly different problem. So we now have x. Oops. We have, sorry, I already kind of forgot it. Integral of cosine times 2r squared. So, integral of cosine squared theta d theta. We have 2 cosines here. That was nice. Times 2r squared. And we're integrating now from negative pi over 2 to pi over 2. Positive pi over 2. Alright, and we've hit another wall. We know what the integral of cosine is. We know what the integral of sine is. But what is the integral of cosine? Alright, every time, this is why I like this problem, and this is also why I avoid this problem to show people, which is you hit so many walls here. Your first wall was, how do you get past the square root? Now we have to get past this square, the cosine squared. Like, I don't know what that is. You might be able to use integration by parts. But there's this cool little ditty called the double angle formula, alright? It says that cosine of 2 times an angle is, man, I need to prove this in like a few videos or something. So cosine of 2 times an angle is equal to, let me remember, it's going to be cosine squared of theta minus a sine squared of theta. There's 2 really cool ways to prove it. One is using imaginary numbers. We'll do that later. But this is called the the double angle formula, because you take double an angle and you convert it into cosine squared and sine squared. Well, what is sine squared? Sine squared is 1 minus cosine squared. We already saw that, right? 1 minus sine squared is cosine squared. So 1 minus cosine squared is sine squared. It's just the same thing backwards. So cosine 2 theta is now cosine. Wait, which one do you want to do? Which one should we replace? Let's pick some. Sorry. Yeah, let's replace sine with 1 minus cosine squared theta. Because that's a squared, so that's nice. So if we replace that, this is a negative 1 minus cosine squared. Let's switch colors. It's getting a little dull. All right. So that's going to be a cosine squared minus a 1 minus a negative cosine squared theta. So now we have a positive cosine squared theta, and so we have 2 cosine squared thetas now. What's beautiful about this? Well, adding the 1 to this side, we have cosine 2 theta plus 1, and then let's divide this result by 2, and you get cosine squared theta is cosine 2 theta plus 1 divided by 2. What's awesome about this? Well, if we can write this guy as this, we're going to have an easier time. So we have 2r squared. We have the integral of pi over 2 up to pi over 2 of cosine squared, which is now divided by 2, so you can factor out the divided by 2. I'm not going to do that just yet. Divide it out yet. And then you have cosine 2 theta plus 1 d theta. So we can finish one of these integrals already. This cancels out. Let's just do that. Now we have r squared times the integral of negative pi over 2 to positive pi over 2. You have cosine 2 theta. We'll fix that guy up in just a second. And then the integral of that guy is just theta. And so theta, the integral of theta, and the integral of 1 is just theta. So you plug in pi over 2. Sorry, this is all bracketed because this is half the integral we're solving already. So from negative pi over 2 to pi over 2. So the integral of 1 is theta if you consider d theta, what you're integrating. So now you have this guy. Wow. Negative pi over 2 to pi over 2 of cosine 2 theta. This orange is getting to me, but let's finish with it. D theta. And then you have pi over 2 minus a negative pi over 2, which is what you think? Pi. This is interesting. So you can expect, all right, just bear with me here. A cosine 2 theta is just going around a circle twice as fast, right? That's literally what it means in a visual context. So if we draw this circle and we go around pi over 2, well, we've actually gone around 2 pi, right? If you plug in pi over 2 into this, we've actually gone to pi. So if you take cosine starts at 1, goes to 0, then goes to negative 1. All right, that's our graph of it. We're just solving this visually for a second. Well, you can expect it would keep going. Yeah, we already know that. But this 0 point usually happens at pi over 2. But if you push it at 2 times the speed, this is now pi over 4. And guess what this is? This is pi over 2. Why do I bring this up? Well, check this out. This right here is a positive area. This right here is a negative area. They're directly symmetrical. And so if you add the same positive area to the same negative area, you're going to get 0. Cool? Let's prove it using integrals, just because I don't want to cheat here, kind of, because we're already doing some crazy stuff, but you can expect this turns in pi r squared. Let's just check this. Cosine of 2 theta. So pi over 2, pi over 2, cosine 2 theta d theta. All right, in order for this integral to work, you need a 2 here, and if you're going to have a 2 here, you have to have a half back here. All right, so cosine of 2 theta, the derivative is right here, so you can rewrite this as, let's write it with u's, cosine of u, right? Because du was on the outside. The 2d theta is the same as du, because that's the derivative of that guy. And then that's from negative pi over 2 to pi over 2. All right, and that's half. So now plugging, what's the integral of cosine? Well, the integral of cosine is sine. In fact, it's negative sine. So it's negative sine u. Now, the only difference is that because we plug in 2 theta here, again, this is a substitution thing. I just kind of didn't want to write out the substitution, but I guess I should. This guy gets multiplied by 2, and this guy also gets multiplied by 2. The reasoning being is because we substituted a value that was 2 times the angle. So we have to multiply those angles by 2. So we're now solving sine, negative sine u. Is it negative sine? No, I think it's positive sine. I think. Yeah, derivative of sine is cosine, so integral of cosine is sine. All right. From negative pi over 2 times 2, so that's negative pi to positive pi. You should see what's happening. All right, sine plug in pi. All right, minus sine plug in negative pi. And all this is times half. Well, sine plug in pi, what's the y value at an angle of pi? Well, that is 0. So this guy is 0. And what sine plug in on negative pi? Ooh, look at this. This is also 0. 0 minus 0 is 0. 0 times half is 0. So this is still equal to 0. Plug that in as 0, and you get 0 plus pi. 0 plus pi is pi. Pi times r squared is a pi r squared. So the integral of 2 r squared minus x squared dx from negative r to r is pi r squared. Beautiful. All right. I recommend you try this for yourself, except for, what would happen if we took an indefinite integral, where we didn't define the bounds of this curve, and we'd have to reconvert an end? I really recommend that, but it's also a really hard problem, so have fun.